Welcome everyone. In this lecture, I will talk about Savin's and Eyring's formulae. In my previous lecture, I talked about the introduction of acoustics, its basic properties and importance, and reverberation time. So in this lecture, I will talk about Savin's and Eyring's formulae and the absorption coefficient of sound. So Professor Savin was the Acoustian to study reverberation around the turn of last century. He actually designed the Boston Symphony Hall, which you saw in the previous lecture. He determined the reverberation time of empty halls and furnished halls of different sizes and arrived at the following conclusions: that reverberation time depends on the reflecting properties of the walls, floor and the ceiling of the hall. The reverberation time depends upon the volume of the hall. The reverberation time depends on the absorbing power of the various surfaces, that is carpets, cushion, curtains, etc. The reverberation time depends on the frequency of the sound. Nevertheless, the reverberation time is independent of the position of the source and the listeners, that is the shape of the room. So, depending on all these conclusions, Professor Savin summarized his result in the form of the following equation, that is reverberation time is equals to volume of the hall divided by the absorption. Here absorption is the total absorption. So T is equals to V by A, or you can write it as K into V by A, where K is a proportionality constant whose value depends upon the units which the length is measured. If the length is in feet, then K is equals to 0.05, and if it is in meter, then K is equals to 0.161. So you can write that T is equals to 0.05 into V by A when the length is in feet, or T is equals to 0.161 into V by A when the length is in meter. So these equations are known as Savin's formula for reverberation time. Now, when you have n number of surfaces to absorb the sound, you can rewrite the Savin's law, or you can write that T is equals to 0.161 into V divided by summation over alpha n into Sn, where alpha n is the absorption coefficient of the nth surface and Sn are the surface area of different surfaces in square meter. As V, S and alpha can be calculated from plans and specifications, so it is possible for an architect to design the auditorium with any desired time of reverberation. So now, whenever I am explaining this Savin's formula or the reverberation time, I always talk about the absorption of sound or the absorption coefficient of sound. So now, what is the absorption of sound? The property of a surface by which sound energy is converted into other form of energy, let's say to heat, is known as absorption. It is mainly due to two causes. So one is porosity. In the process of absorption, sound energy is converted into heat due to the frictional resistance inside the pores of the material. The porous materials absorb sound energy more than the solid materials. And the second one is flexural vibration. When sound waves fall on flexible materials, not rigidly mounted, the material of course is set into vibration, and the damping forces called into play dissipate the incident sound energy into heat. So when these materials actually absorbing sound, there must be some coefficient of absorption, and we actually express this coefficient of absorption as alpha. So alpha of a material, that is the absorption coefficient of a material, is defined as the ratio of the sound energy absorbed by its surface to that of the total sound energy incident on the surface. So you can write that alpha is equals to sound energy absorbed by the surface divided by the total sound energy incident on the surface. Therefore, the unit of absorption is the open window unit, which is named Savin after the scientist who established the unit. 1 meter square Savin is the amount of sound absorbed by 1 square meter area of fully open window. The value of alpha, that is the absorption coefficient of sound, depends on the nature of the material as well as the frequency of sound. It is a common practice to use the value of alpha at 500 Hz in acoustic designs. If a material has a value of alpha is equals to 0.5, it means that 50% of the incident sound energy will be absorbed per unit area. If a material has a surface area of A square meter, then the absorption provided by the material is A is equals to, which is the total absorption, is equals to alpha into S. Alpha is the absorption coefficient and S is the surface area in square meter. However, there are some limitations of Sabin's formula. It is good for only small values of absorption coefficient, that is when alpha is less than 0.2, and certainly it is not valid for higher values of alpha. For instance, when alpha is equals to 1, t, that is the reverberation time, should be 0, whereas Sabin's formula finds t is equals to k into v by a, and it is actually a non-zero value. So for higher values of absorption coefficient, Sabin's formula gives higher value of reverberation time than its actual value. And that is why Eyring's formula came into existence. Eyring actually considered the same assumptions as has been considered for Sabin's case, and with considering all those assumptions, he told that t is equals to, that is the reverberation time is equals to 0.05 into v divided by minus s into log with base e 1 minus alpha, where 1 minus alpha is actually the fraction of energy reflected, that is the average reflection coefficient, and that is 1 minus alpha. And this formula, when you consider the length in feet with the velocity of sound is 1120 feet per second, and when you consider the length in meter, that is when the velocity of sound is 340 meter per second, reverberation time is equals to 0.161 into v divided by minus s into log with base e 1 minus alpha. And for the both cases, alpha is the fraction of energy absorbed, that is the average absorption coefficient, and 1 minus alpha is the fraction of energy reflected, that is the average reflection coefficient. So now if we want to compare the Sabin's formula with Eyring's formula, so what we can see here, that for Sabin's formula t is equals to, that is the reverberation time is equals to 0.05 into v divided by s into alpha, whereas for Eyring's case t is equals to 0.05 divided by minus s into log base e 1 minus alpha. So basically both formulae give identical value when the alpha is small. Nevertheless, for large values of alpha to give different values of t. So for example, if you considered alpha is equals to 1, then reverberation time using the Sabin's formula is equals to 0.05 into v divided by s, which is a non-zero value. But if you use Eyring's formula, you can get that t is equals to 0, which is actually the expected case when you considered alpha is equals to 1 and reverberation time is equals to 0. Since for alpha is equals to 1, there is no reflection of sound energy, that is the total reflection will be equals to 1 minus alpha, that will be 1 minus 1, so equals to 0. There is no reverberation time, of course, so Eyring's formula gives correct results. So that's all for today, and in the next class I'll discuss about methods to measure the absorption coefficient and applications of acoustics, that is designing of hall or concert hall and opera.